Okay, so last time we talked about language modeling using neural networks, neural language modeling. Previously, we did this with the statistical language modeling, and we compared these two together. Okay, question for you: what is the main difference between in terms of advantages and disadvantages? What is the main difference between neural language modeling and the statistical language modeling? Maybe I should make a small table. Statistical language modeling and neural language modeling. You know, the statistical language modeling is based on n-grams, right? This one is okay, neural networks. We know that, okay? So what is the pluses and the minuses for statistical language modeling? Pluses are, it's very easy, right? Very, very easy, convenient, very simple structure, just calculation of the n-grams, that's it. What is the main minus? Calculations of, it is easy, but what? In terms of training, you mean, right?
It means loss of memory.
Loss of memory, and it is slow because you need to process lots of stuff. Okay, needs memory. Needs memory and slow in terms of data processing. Okay, that's good. And with the pluses, can work with small data. Small data. Just a few thousand sentences, and up to some point it can work. Okay. So what are the pluses for the neural language modeling? Remember, the neural language model it's a neural network. It can guess what the next word is using the neural network. Okay. Pluses is okay. Again, it is not labeled, and it is not labeled data. You just give the complete sentences and it trains by itself. Not labeled, again, like the n-grams, not labeled. But the plus is it doesn't need lots of memory, less memory. Less memory, right? And less memory means that it generalizes better. Okay. Those are the things. What are the minuses for the neural language modeling? Needs lots of data. With maybe this needs memory is kind of, if you are smart, maybe you don't need lots of memory, but how smart you are doesn't matter. This data sparsity is going to be a problem. I mean, 99.999% of your 5-gram tables will be empty, right? Okay. So generalizes better, and no sparsity issue. Okay, no sparsity. Sparsity, and one other thing, neural network, difficult to debug. Why? Because if what?
It's not impossible.
Well, I mean, I wouldn't say impossible. Sometimes you find what is wrong with it. But if you get some nonsense answer out of your neural network, then you don't have any choice but you accept it. Well, it behaves this way. You kind of say that. Okay, so statistical language modeling and neural language modeling are like this. But nowadays, whatever the minuses of this thing is, neural language modeling, they are definitely preferred over this statistical language modeling, whatever area look at it. And maybe it wasn't like that maybe 5 years ago. It was a little bit different. It was like maybe hybrid methods between statistical language modeling and neural language modeling were kind of, they are doing okay. But nowadays they are definitely much better than whatever we had before. So that's kind of a summarization of what we did last time. Okay. So the basic neural language modeling structure is like this. Okay. Remember what we did? This was a neural network that we did for the named entity recognition problem, and we are saying that why don't we use this to calculate the probabilities of the next word. This is what we did, right? So I input 1, 2, 3, 4 words, and I'm trying to guess the next word. Okay. So out of all the words in my dictionary, books and laptops, they will have the higher probability than the others. Okay. I have a softmax layer at the top, softmax layer, and these are this hidden layer is, okay, W is my weight matrix, okay, and this is my input, E, and this is my bias, and I feed it through some kind of a nonlinear function, and the most popular, the most widely used nonlinear function is ReLU, rectified linear unit, and then we have the softmax. Softmax is, we already know, produces a distribution for each class, and it doesn't matter how many classes you have in your dictionary, how many words you have in dictionary, the summation of all the probabilities will add up to 1.0. Okay, that's the softmax stuff. We already know that. Okay, we looked at all of these, and later we said that, okay, this one can take this input and produce one output. Okay, but this only works for 1, 2, 3, 4 inputs. What if my input sentence is longer than 4? Usually it's going to be. What if it is 5, 6, 10, 8? And what if I don't want to restrict myself to certain number of inputs? What am I going to do? Then we have invented this recurrent neural networks, right? Recurrent neural network says that, okay, give me your input, I am going to output something, and then give me your next input. Next input will be affected, okay, your network will be affected from your next input, also my current internal state. Okay, current internal state, and I'm going to give you an output. And for the next input, my current internal state, and I will be affected from both what I said before, both what I have said before, and my current input. So that means what? For this kind of a network, my input is kind of infinitely long. Doesn't matter how long it is. For every input, by looking at whatever I said before, I can output something. So this is called recurrent neural networks, and people knew about this a long time ago, from 1990s, and still we have been using it. Still different version of this recurrent neural networks. Okay, so that was the nice thing about it. The plus of the recurrent neural network is RNN. Okay, plus is, okay, arbitrary length inputs. Okay, that's the plus of it. I can process arbitrary length input, including 3, 4, 5 words to up to 50, 100, 1,000 words. Doesn't matter. It's going to work. What is the minus for the RNNs? What is the minus for the RNNs?
It remembers the last word better.
What's that?
It remembers the last word better.
It gets affected by the last word more?
Yes.
Well, yeah, sometimes you want it, but sometimes, yeah. Okay. Okay, recency. The tendency for, okay, we call it recency. recency, I don't know how to write recency, but I guess it's like that. So it is more like, if my input is the students open there, right? The students open there, it is more affected from this word than this word, right? That's the recency of problem. But before coming to that, there is another serious problem with the recurrent neural network, as I describe it in here. Yeah, it is about training. Training is difficult. Difficult to train. Difficult to train because of the vanishing gradients.
Hard to parallelize.
And it is very hard to parallelize. Hard to make them parallel. Right? How to make them because I mean, if I have a 1 million word corpora, I need to feed it through this loop, through this pipe, okay, pipeline, starting from the first word and the second and third, and it goes that way, okay? I cannot say that I am going to process 100 word sections, 100 sentence sections in parallel. It is hard to parallelize. And in deep learning world or the neural network world, if you don't parallelize stuff, then your training will be very, very slow. But still, it is nice. It works very well for many cases. We get lots of nice stuff. And the basic thing is here, okay? So what do we say? I have a weight set for my input. This is my input at time t. I have a weight set for my internal state of t minus 1. Okay, learn this weight set and learn this weight set, add my bias, and run my sigma or or determine my internal state for the next case. Okay, so H0 is usually the initial hidden state. Can you tell me what H0 could be? Okay, in this case, the students opened and this one, the students opened there and this one is supposed to be either books or laptop. I don't know what the inputs are. Can you tell me what kind of input what kind of data can I include in the H0? Yeah.
Maybe it means the start of the sentence.
Well, I mean, start of the sentence would be my first input then.
Right.
You mean that like this, right? \s.
Yes.
Yeah, that would be my first thing then. That's the word, right?
Trained variables.
What?
Trained variables.
What do you mean? What is our problem? Our problem is, for example, is guess the next word, right? The students open their books or laptops or whatever, okay? Maybe I can give context information from this end. Maybe I can input, for example, the vector of my context. For example, if the students open if the students are computer engineering students, maybe it is laptops. If the students are, for example, the primary school students, maybe it is books. If the students are, for example, basketball students, maybe they open their bags, right? So maybe I can give the context information for this H0. And in fact, this part is so convenient. Maybe I don't have it on these slides, but I am going to show you this. Image captioning by RNN. People do this. Yeah. If I go there, okay, somebody's giving this, okay. Automatic image captioning using deep learning, CNN, LSTM, both of them are, of course, these are RNN versions. Okay, go there, skip this one, close this one. I am ready now. Okay. So this is a classical picture. This is a classical picture. You do this. Okay. You get your image. Okay, you get your image. You get a 4,000 dimensional vector for this image. Okay, I converted this image to a 4,000 dimensional vector, and I input this as my initial state. Then I ask this network to produce a caption for me. Okay, and it produces this caption. It says that given this, okay, it says giraffe standing. Okay, and end of the sentence. See this one. What you are suggesting is beginning of the sentence. The beginning of the sentence is here. Okay, so I train it this way, and what I do is I get this image, I feed it through some kind of a image processing, image classifier network, and this one, instead of producing a classification result, it produces a two-dimensional vector, and I input that two-dimensional vector as my H0, and I say that this is your start. After the start, you are going to produce giraffe. After the giraffe, you are going to produce standing, and after that is going to and if you are going to produce and. Okay, that way it's going to work to some degree, and yeah, this is what it. A group of giraffes standing in a grassy area. Okay, this is how you train it, and this is. Did you get any results? No, I didn't get any results. But you are going to get results like you are going to get results like. Can I show you some results? Examples. Yeah. For example, this one. A cute little dog sitting in a hard-drawn on a sandy beach. It is not impossible to get this kind of captioning out of this image. Okay, so of course I am not trying to tell you detailed stuff about the image processing with deep learning or RNNs, but this is what I am trying to tell you. Okay, this H0 kind of gives you the context of the sentence. Okay, so that's where it can come from. So what are the disadvantages? Recurrent computation is slow and difficult to access information from way steps back, and we will come to that one later. And these are the advantages. Can process any length input, computation for step T, use information from many steps back. It is not only 4 steps back. Okay, and model size doesn't increase for longer input. If your input is 1,000 words, then my model size is the same, WE and WH. That's it. Because this one is same as this one, and same as this one, and same as this one. Okay, good. We talk about these and vanishing gradient problem. I am not going to repeat that again. And these are some of the RNNs as language generator examples, RNNs as code generators, and etc. And we talked about the perplexity, and we said that if you are talking about perplexity, neural network modeling, neural language modeling is way better than the others. And at the end of this one, yeah, we said that we are going to look at the other types of neural networks. Okay, let's look at other types of neural networks. Okay, recurrent networks, okay, they are great for language modeling, and today we are going to look at some of the variations of the RNNs. Okay, and then we will start talking about the neural language translation. Okay, LSTM and GRU are 2 new types of RNNs. GRU is actually a subset of LSTMs. LSTMs are more general than GRUs. GRUs, we say that They are good if you don't have enough data. Okay? So we said that one of the problems with RNNs is the vanishing gradients. Okay? Vanishing gradients. What is vanishing gradient? If you have a very deep network, between the result of your network and the input, there are many layers of neural networks. Then we run into this vanishing gradient problem, because due to the chain rule of derivatives, we have to take many derivatives, and derivatives are small numbers. If you multiply those small numbers, they will get smaller and smaller and smaller, and that may cause some underflow in my system, or those numbers are very slow. My gradients will be very small numbers. With the small numbers, gradient descent will not work very well, right? It's like this. If you have a function like this, my gradient angles will be very steep, and I can move to the local minimum in a very fast way. But if you have a function like this, okay, starting from this area, your slope is it is parallel to the x-axis. Your movement at each gradient descent step will be very slow. So since it's going to be slow for this one-dimensional problem, it's going to be exponentially slower for the 1,000-dimensional problems. So that's the vanishing gradient problem. We don't like this kind of a thing happening for our training. That's why it's going to be a big problem. The other thing is this. It's called exploding gradient. If my function is like this, then in this case, my derivatives will be very steep, and I will overshoot. Okay, if I am at this position, if I move along this gradient, maybe this much, okay, I will overshoot and I will come to this position. Okay, and I may lose the local minima or the global minima. That's called the exploding, okay, gradients, and it's going to be a problem, a similar problem that we should take care. Okay, the solution that I'm going to tell you, the LSTM and GRU, is going to address especially the vanishing gradient problem. For the exploding gradient, we are going to have some other solutions. Okay, typical network, first layer, second layer, third layer, and the fourth layer. Okay, and if I am trying to get this derivative of this loss function with respect to my weights here, okay, then I need to take the derivative of with respect to this one, derivative of this with respect to this one. So I keep doing this chain rule multiplication, as I said before, multiply, and multiply. If these values are small, this value will be very small. Small means that I cannot get large steps between the gradient descent algorithm steps. Then that's the vanishing gradient problem. When these are all small, the gradient signal gets smaller and smaller as it propagates further. This will either cause numerical problems, like the underflows, or my training will get very slow. Okay, so that's one thing. Vanishing gradient problem. The other one is, okay. The other one is, okay, maybe I can, you might say that, why is it a problem? Because if I go only 1, 2, 3, 4 steps back and optimize network that way, this may not be a that big problem. I mean, just go 4 steps back. Since I am moving my window from word window to word window one by one, I will take care of all the words one by one, but if you look at this one, okay, just look at this sentence. When she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her what? Her what? Her what?
Page.
Tickets. But when was the last time I have seen tickets?
In the first time.
It was like here, right? So when I am calculating this word in my language modeling, I need to backpropagate that information over this 1, 2, 3, 4, 5, 6, like 40 words back, right? So I need to multiply 40 small numbers together to derive the optimization for selecting this word so that it gets affected from this word tickets way back. Okay, so that's not going to be that easy if I have the vanishing gradient problem. So I mean, your suggestion or my suggestion of just use a window of 4 isn't a good suggestion. In that case, I am not going to handle this kind of an error. Okay, so usually when I say she finally printed her, usually it finds the nearest noun and it replaces it with the nearest noun. Usually it says she finally printed her printer, or she finally printed her toner, or she finally printed her store, or etc. toner, etc. Okay, so that's what it does, and that's not going to be a good thing. Okay, and so this is the recency problem. If you train your system like that, the nearby words are going to affect your final results more. The writer of the box, okay, when you say box, usually if you are training an RNN, the tendency is you say are, the writer of the books are, but in fact the correct thing is, right, because writer is. Okay, so we know these kind of problems. People noticed it, 2016. Okay, another thing is the exploding gradient. Exploding gradient is this. Okay, you measured your gradient, it is too big. If it is too big, you are going to move your search to some very distant place where your solution does not exist. Okay, you don't want to do that. You don't want to move your search to some unrelated place. That's kind of wasting all of the time that you have calculated. That's too big. It's like this. If you take the gradient at this position, very steep edge, okay, it's going to be a very, very big jump. You are going to lose this local minima. This is my local minima here. It will move way over the edge. So that's called gradient exploding gradients. For that one, we do clipping. So what we do is, you get your gradient vector length, and you clip it to a unit length or something like that. Okay, so clipping gradients is something that we do to handle the exploding gradients. That's one easy solution, effective solution. For the vanishing gradients, we don't have that kind of a easy solution. For the vanishing gradients, this is what we are going to do. For the vanishing gradients, we are going to say that, why don't we have direct lines between this one and this one, and this one and this one. This way, when I take the derivative of this loss with respect to h1, okay, I don't have to go through all these weights, all these steps. I can take it with respect to that one. Of course, there is another line here, but if I take it with respect to that one directly, vanishing gradient problem will be addressed somehow. Also, I am relating this distance word with this current loss function, and that's going to make my job easier in terms of relating two distant words together. Okay, that's the idea of the LSTM. That's the idea of the LSTM. That's what we are going to do in a few minutes. Long, short-term memory. Two types of memory, short-term memory and long-term memory. They say that this is motivated from the mammals' memory mechanism in our heads. I don't know how true it is, but in practice, whatever we are building kind of works. Okay, it works better than RNNs. Okay, on step T, there is a hidden state and there is a cell state. Remember, usually we had in RNNs, we have only the hidden state. Now we have the cell state, second one. So there is one vector H, another vector C. Okay, both are vectors of length n. The reason why they have the same, the reason why we have the same vector length will be apparent in a few minutes, if I can. Okay. So we have two states in our network now, hidden state and the cell state. Okay. The cell stores long-term information, this one, long-term information. We are going to connect words from a long distances, long-term information. That's how human memory works, they say that. And sometimes we remember long-term information that are important. Sometimes we forget. Short-term information is always important.